Hi, this is Kaylee, and let's talk about the work-energy theorem. The work-energy theorem is a really handy piece of information. It basically talks about how work is the mechanism which causes energy to change. And so if you do work on an object, you're going to change its energy or change the situation somehow. So if we do work lifting something, we're going to change its potential energy. If we do work pushing something, we're going to change its kinetic energy, roughly. Okay. So there's a lot of different situations that can go on, but in generally, if we're making something move quicker or slowing it down, we're changing its kinetic energy. If we're changing its elevation, we're changing its potential energy. So one way that we can express work is simply the change in energy. So on this example, if I do 150 joules of work lifting an object, it started off at 0 potential energy. I lifted it doing 150 joules of work to it. It now has 150 joules of potential energy. If something's moving, or even if it's sitting still, and I push it to make it go faster, and I do 150 joules of work to make it go faster, I've increased its kinetic energy by 150 joules. Let's look at some other applications of this. Okay, in this situation, we have got a mass at different heights above the ground. Let's start off with this one. It's 12 kilograms, 6 meters above the ground. So if I want to find its potential energy, it's simply 12 times 9.8 times a height of 6. And we get a potential energy of that object to be 12 times 9.8 times 6, 705.6 joules of potential energy. Now, we've got the same block now moved 12 meters above the ground. So we could calculate it again like we just did, but let's take a look at it. We're at twice the height, same mass, so we should have twice as much potential energy. So it'll be this simply times 2. We've got something that's the same height as this one, but it has half the mass. So if it has half the mass at the same height, it should have half the potential energy. So we can just take that and divide by 2. So we can use this idea about work. Like, which one of these required the most work? Well, that one, because it's the biggest mass, highest off the ground. Which one required the least work to put in that position? Will be this one, because work would be equivalent to the potential energy of that object at those heights. Let's look at work and kinetic energy. All right, so for this one, we've got a car. Well, all these are the same car, to the best of my drawing ability. And with this amount of kinetic energy, it stops in 1 meter. Well, what if the speed is doubled? Well, if the speed is doubled, what happens to the kinetic energy? Well, kinetic energy is 1/2 mv squared. So if that stays the same in velocity squared, 2 squared is 4, so the kinetic energy is going to be 4 times as much. Or in this case, 4 times 1,000 is 4,000 joules. If the braking force was the same, how far will the car go before it comes to a stop? Well, we can actually calculate it. We can do that, figure out what the force was, then determine the distance, or we can use this idea about work and kinetic energy. So if the kinetic energy is 4 times as much, then the work has to be 4 times as much to stop it. Well, if the braking force is the same, the only way we can make up that addition of 4 times is having 4 times the braking distance. And this is not drawn to scale, but it would take 4 times that distance to stop in. Well, what if we triple the speed? If we triple the speed, again, mass stayed the same, but V is now 3 times as much. 3 squared is 9. So the kinetic energy would go up by a factor of 9. And so it would have, if we wanted to know the number, 9,000 joules of kinetic energy. Well, that means the brakes have to do 9,000 joules of work to stop it. And if the braking force is the same, The only way we can get 9 times as much is to go 9 times the distance. So 9 meters. So remember, work changes energy. It can change its potential energy, kinetic energy, really can change both at the same time. But we really only are interested in at the endpoints with work and energy. We don't care exactly what happens in between. We just want to know its starting location and its ending location, or starting situation and ending situation. So, thank you very much for watching this video, and we'll do some more physics later on. Goodbye.